Before bones, before forests, the planet was almost unrecognizable. The young Earth glowed beneath a sky without oxygen. Volcanoes stitched fire across black horizons and newborn seas. Meteorites still struck, shaking continents that barely existed. Yet somewhere in that violence, chemistry learned a new trick. Dead matter began edging towards something eerily alive. No witness saw the first true beginning happen. Only stone, isotope, and ancient carbon whisper back. From those fragments, scientists rebuild the strangest dawn imaginable. And every answer opens another darker, deeper question. First came the stage itself. A molten planet cooled, crust formed, cracked, and vanished. Earth was not stable. Oceans may have appeared early. Ancient zircons hint at water. Those crystals are tiny. Their message is enormous. Liquid water existed astonishingly soon. That changes everything. Water slows, carries, and gathers chemistry. It makes experiments possible. But early Earth stayed dangerous. Impacts churned seas. Heat and ultraviolet hammered every surface. Life may have started more than once. Some beginnings probably failed. The rocks barely remember. Where did success happen? In tidal pools or deep below waves? Scientists still debate it. The evidence is indirect. The mystery remains alive. One idea begins in soup. Lightning energizes simple gases. Molecules assemble unexpectedly. The famous Miller-Urey experiment showed that possibility. It made amino acids. It did not create life. Modern researchers add caution. Early air was likely different. The experiment opened a field. Another path descends deeper. Hydrothermal vents leak hot minerals. Chemistry meets strong energy gradients. At alkaline vents, tiny pores form. Mineral walls create compartments. Nature sketches primitive cells. Those stone chambers matter. Life meets separation. Inside and outside must become different. A membrane solves that. It holds reactions together. It lets selection begin. But membranes alone are not enough. Life must copy information. It must also harvest energy. Here, the puzzle sharpens. Which came first? Metabolism, membranes, or genes? Many scientists favor partnership. Several systems may have co-evolved. Simplicity arrived in layers. RNA enters the story here. It can store information. It can also catalyze reactions. That makes RNA alluring. One molecule does two jobs. Perhaps early life relied on it. Yet RNA is fragile. Building it is difficult. The first steps stay uncertain. Life also chose handedness. Amino acids in life lean one way. That bias remains mysterious. Tiny asymmetries can snowball. A slight preference spreads. Order emerges from imbalance. Clay offers another possibility. Its surfaces gather molecules. Crowding can encourage assembly. Minerals do not reproduce, but they can template chemistry. Even a passive scaffold helps. So researchers test alternatives. Peptides, lipids, minerals, and cycles compete. No single answer rules. Maybe sunlight-powered surface chemistry. Maybe volcanic lightning helped. Maybe wet-dry cycles concentrated ingredients. In drying ponds, molecules crowd together. Bonds form more easily. Returning water reshuffles the mix. In icy settings, paradox appears. Cold can protect molecules. Thin brines still allow reactions. Early Earth offered many laboratories. Countless failures vanished. One lineage kept going. We should picture no miracle. Picture repetition instead. Trillions of blind chemical trials. Most combinations dissolved. Some persisted longer. Persistence is the seed of selection. Once a system copied imperfectly, everything changed. Error became opportunity. Variation could matter. Natural selection in some form may have begun, not with animals, with chemistry itself. The first true cells were not alone for long. They diversified quickly. Competition already had meaning. Yet those pioneers were simple only by comparison. Even a bacterium is astonishingly complex. That is why origins feel strange. The gap seems impossible. Chemistry somehow crossed it. We may never find the exact place. Earth recycles its earliest crust. The first stage is mostly gone. But life leaves shadows. Carbon isotopes shift subtly. Rocks preserve improbable patterns. In Greenland, ancient sediments carry debated hints. Their chemistry looks biological. The argument is ongoing. In Australia, stromatolites stand clearer. Layered microbial mats built them. Some are about 3.5 billion years old. Imagine no leaves overhead, no birds call, only microbes film the shore. They spread as slick carpets. Sediment sticks to them, layer by layer, stone records breath. These worlds were quiet from afar. Up close they were busy. Cells traded molecules constantly. The atmosphere then felt alien. Oxygen was absent or scarce. Methane and carbon dioxide loomed larger. Seas held dissolved iron. The water chemistry differed sharply. Entire oceans behaved unlike ours. Sunlight still mattered, but early photosynthesis probably began without making oxygen. Life learned slowly. Some microbes ate chemicals directly. Iron, sulfur, and hydrogen fed them. Sunless ecosystems were possible. That is another startling truth. Life does not require green forests. It only requires usable energy. Deep below waves, modern microbes survive near vents. They are not living fossils. They still inspire hypotheses. The last universal common ancestor comes later. It was not the first life. It already inherited long history. By then, basic machinery existed. Genetic code worked. Cells already managed membranes and metabolism. Some scientists emphasize proton gradients. Modern cells still use them. The similarity may be ancestral. Across membranes, unequal charges store energy. Life exploits that difference. Chemistry can act like a battery. Early systems were probably leaky. Precision came later. Survival only needed enough stability. Before neat species existed, genes may have mingled. Early evolution was communal. Boundaries sharpened slowly. So the true origin lies earlier. Before shared ancestry, before the tree had a trunk. We are tracing smoke backward. Each clue gets older. Each certainty gets thinner. Still, patterns converge. Water mattered early. Compartments mattered. Energy gradients mattered. Carbon mattered too. It bonds flexibly. Life uses that versatility everywhere. Phosphorus helped link molecules. Nitrogen shaped proteins and bases. Metals nudged reactions along. Nothing here looks magical. It looks chemical, yet chemistry arranged itself into inheritance. That transition may be the strangest event ever. It happened once here, or once that survived. Imagine the patience required. Millions of years pass. Still the experiment continues. Tides rise and fall. Vents pulse and cool. Molecules meet, separate, and meet again. Somewhere, a boundary stabilizes. Somewhere, copying improves. Somewhere, chance stops being enough. If you had to choose, where would life start? In sunlit shallows or dark vents? Tell me below. I want your best guess. Then we keep going. Because the next change is planetary. Life stops merely surviving, begins remaking Earth. Cyanobacteria master water and sunlight. They release oxygen. At first, that oxygen disappears. It reacts with iron. Rust rains to sea floors. Banded iron formations accumulate. This shift was not instant. Oxygen rose, faltered, and rose again. Geology kept score. The Great Oxidation changed every future chapter. New metabolisms became possible. Old worlds retreated. Oxygen also helped form ozone. Harsh ultraviolet softened somewhat. New surface niches gradually expanded. But oxygen remained double-edged. It empowered rich metabolism. It also ruined older lifestyles. Without that microbial revolution, animals never appear, forests never spread, breathing bodies never happen. Yet cyanobacteria were not aiming for us. They were simply living. Consequences arrived anyway. That is deep time's irony. Small lives alter planets. Grand worlds begin invisibly. The strange beginning of life is not thunderous. It is cumulative. A whisper becomes atmosphere. Long before skeletons, microbes engineered coasts. They trapped sediments, They built reefs unlike coral. Some stromatolites still live today. Rare modern analogs survive. They echo ancient strategies. Stand beside one now. You are looking sideways through time. The shape is familiar. But the early planet beneath it was not. Days were shorter. The sun itself was dimmer. Despite that fainter sun, Earth had liquid water. Greenhouse gases likely helped. The balance was delicate. Continents were smaller then. Oceans may have dominated. Shorelines shifted across a restless world. Meteor impacts kept coming. Some may have sterilized regions. They also delivered fresh material. Space may have supplied organics. Meteorites carry amino acids. Cosmic chemistry joins the story. That does not mean aliens seeded Earth. It means ingredients travel. Planets are not chemically isolated. The universe makes building blocks widely. Earth provided persistence. That combination may have been enough. Even so, enough remains uncertain to stay humble. Scientists test scenarios constantly. Confidence has boundaries. We do not know the first genome. We do not know the first membrane. We do not know the first habitat. We may never know the exact moment. Origins leave sparse evidence. Time erases its own footprints. But uncertainty is not emptiness. It narrows possibilities. It tells us which worlds could work. That matters beyond Earth. Every origin question becomes an astrobiology question. Could it happen elsewhere? If water appears quickly, hopes widen. If chemistry self-organizes readily, hopes widen further. We keep looking. Mars once had rivers, icy moons hide oceans, exoplanets crowd distant stars. Yet the only confirmed living world is this one. That makes our beginning precious and stranger. Consider how long life remained microscopic. For most of Earth's history, no animal ever swam. No tree cast shadow. No flower opened. The planet belonged to unseen chemists. They invented the future silently. Respiration, photosynthesis, fermentation, cooperation. Every later body borrowed their solutions. Even your cells remember them. Mitochondria descend from ancient symbiosis. Old bargains live within you. Your blood depends on oxygen. Oxygen was a microbial aftereffect. Human breath carries ancient consequence. Every meal continues that story. Stored sunlight meets respiration. Metabolism links us to archaic seas. So when we ask where life began, we also ask something intimate. How did it eventually become us? The answer is not a ladder. It is a branching experiment. Most branches vanished. Survival never meant inevitability. A slightly different chemistry, and we might not exist. Deep time allows no guarantees. That is why the opening feels uncanny. Life is ordinary now. Once it was nearly impossible. Yet once it started, it endured. Asteroids struck, continents drifted, oceans froze and reopened. Lineages adapted, merged, and radiated. Extinction shaped them. Persistence shaped them more. The first cells never saw trilomites. They never saw dinosaurs. They still made both possible. They also made forests possible. Birds, whales, and primates followed. Complexity arrived late. Humans appear almost at the final second. We inherit a planet pre-written by microbes. Our prologue is unimaginably long. And that prologue began in darkness, not evil darkness, creative chemical darkness. Hot water, mineral walls, and restless shorelines. Lightning, tides, and impacts. Earth kept mixing possibilities. At some point, matter started remembering. That may be life's deepest definition. Information persisted through time. Once memory existed, evolution could write. Errors became novelty. Novelty met selection. From there, the impossible became history. Cells became ecosystems. Oceans became biographies. But the very first page remains torn. We read around the missing lines. Science advances that way. Each zircon, fossil, and isotope helps. None tells the whole story. Together, they narrow wonder. Maybe the first living system was simple beyond imagination. Maybe it was already surprisingly intricate. Either way, it worked. It worked well enough to outlast fire, well enough to outlast ice, well enough to outlast silence. And after billions of years, it produced observers, creatures who can question the beginning, creatures like us. Would you survive one day on the early Earth? Tell me below. I want to know. Subscribe and ring the bell. More journeys await in the lost worlds before us. We arrived last. Life wrote the prologue. Stone is still whispering it.